Segment 4b, the sun's motion on the sky and the reason for the seasons. We begin with an outside view of the Earth's orbit around the sun. In this picture we see the path of the Earth given as the white circle around the sun, and we note that the Earth's axis, the line going through from the north to the south pole, is tilted by 23.5 degrees from the plane of the Earth's orbit, the ecliptic plane. And this tilt is the reason that we have the seasons and the reason for the change in the motion of the sun through the sky throughout the year. In the foreground, we see the Earth at the autumnal equinox, at the time when the pole is pointed neither towards nor away from the sun. And then 3 months later, on the right, we see the winter solstice, when the north pole of the Earth is tipped away from the sun. 3 months after that, we're at the vernal equinox. Again, the pole is tipped neither towards nor away. And then on the left-hand side, we see the summer solstice, where the north pole of the Earth is tipped towards the sun. For the purposes of normal everyday life, we can consider the pole as pointing towards a fixed position on the sky throughout the year. Of course, we know over a period of many thousands of years the pole of the Earth precesses, but for these purposes we can consider it to be fixed. When we look from inside, when we imagine ourselves sitting on the Earth, we have the sun moving across the sky throughout the year, being on the celestial equator at the two equinoxes, 23.5 degrees north of the equator at the summer solstice and 23.5 degrees south of the equator on the winter solstice. As we mentioned in the last segment, on any given day you can imagine that the sun takes the place of a star at the particular declination, at the particular distance above or below the celestial equator that it happens to have on that day. And then from that you can divine what the sun's path will be. Let's take a look at some of what we expect the motion of the sun to be at characteristic places on the Earth. So in this first illustration, we're looking at what things would look like at the North Pole. On the vernal equinox or the autumnal equinox, when the sun is directly on the celestial equator, you remember that the celestial equator runs right along the horizon at the North Pole. And on that day, on March 21st or September 21st, the sun moves along the horizon at the North Pole, half above and half below. As we move from the spring to the summer, the sun moves farther and farther north of the celestial equator until it's 23.5 degrees above the celestial equator. So on June 21st, the 24 hours of June 21st, the sun is 23.5 degrees above the celestial equator, and it's 23.5 degrees above the horizon at the North Pole. Then the sun gradually spirals back down. It's light all the time at the North Pole during the months between March 21st and September 21st, until on September 21st the sun is once again half up and half down. The sun continues its southward march until December 21st, when it's 23.5 degrees below the horizon, and it's completely dark. As we move to more temperate latitudes, we can look at the sun's path. It's a little more complex. Remember, the celestial equator starts due east and goes over to due west and rises to a point in the sky that is a distance above the southern horizon of 90 minus your latitude. So at the North Pole it's 0 above there, and 30 degrees north it's 60 degrees above the southern horizon. In the summer, the sun rises north of east and sets north of west and rises to a point higher in the sky than the celestial equator, or north of the celestial equator. What happens on the equinoxes? Well, the sun rises on the celestial equator, so it starts due east and goes due west and gets to a point in the sky that's as high as the celestial equator does at your point on the Earth's surface. The length of the day does vary depending upon where you are and what season it is, and this is because, as you'll remember, larger fraction of the arc of the stars in the northern hemisphere is above the horizon when you're north of the equator, and less of the fraction of the arc of the stars across the sky is accessible below the equator, south of the equator. Here in this illustration, we can summarize the behavior at intermediate latitudes. So the dotted line that you see in the middle is the behavior on the equinox, when the sun will rise at 6 a.m. and set at 6 p.m., rise to a position in the sky as high as the celestial equator does at that point, and be exactly 12 hours above the horizon. In the winter, the sun will rise later, set earlier, and a smaller fraction of the arc is above the horizon, and it rises to a lower altitude. In the summer, the sun rises north of the equator, so it rises north of east, sets north of west, and is up for more than 12 hours. Let's ask a more quantitative question, which is how high in the sky does the sun get in Austin in the summer and the winter, and how high? So with the first question we have to ask is how high off the southern horizon is the celestial equator at the meridian? Austin is about 30 degrees north of the equator. The North Pole, then, the North Celestial Pole is 30 degrees above the north horizon. We go another 90 degrees from that. We've gone 120 degrees from the north horizon, so we're now 60 degrees above the south horizon. So on the celestial equator, objects rise to an altitude of about 60 degrees. In the summer, at the summer solstice, the sun is 23.5 degrees above the equator. 60 degrees and 23.5 degrees is 83.5 degrees. The sun is therefore almost at the zenith, almost straight overhead at noon on June 21st. On the winter solstice on December 21st, which was not so long ago, the sun is 23.5 degrees below the equator. 60 degrees minus 23.5 is 36.5. That's less than halfway to the zenith. At noon, the sun is not even halfway up in the sky at its highest point. These changes through the year are what cause the seasons to occur. When you're directly below where the sun is striking, the sun is very concentrated. But if you're on a portion of the earth that's tilted away from the sun, then the sunlight spreads out considerably. At the summer solstice, the northern hemisphere is more directly below the sun, whereas at the winter solstice, going back to the previous illustration, the light is more spread out. What that means is that the same amount of sunlight covers a smaller piece of ground in the summer. One way to illustrate this is just by thinking of a flashlight. Let's look at this, these two slides. In the summer solstice, the light points almost straight down. It's concentrated in a small area. The winter solstice, when it's coming in at an angle, it spreads over a larger area of the earth, and it can't heat the earth as effectively. And besides, it's not even up for as long either. This next diagram shows you that in more quantitative terms, showing that when the sun comes straight down, it covers a small area, and as it comes at an angle of 60 degrees, it covers 1.16 times that area, and when it comes at 30 degrees, it covers twice that area. So the same sunlight is spread over twice as much ground in winter as in summer at a latitude that's only somewhat north of here in Austin. So that's a very big difference, and that's the reason why it's cold in the wintertime.